Hello. This will be our final lecture on operational amplifiers. It will cover pages 87 through 92 of my lecture notes. So please print those pages out and have them in front of you as I present this lecture using the op amp for set point triggers. If you take a look at page number 87, we're going to look at the operational amplifier back in an open loop mode. There's no feedback in this part of the lecture. This is going to be the only time that we talk about the operational amplifier, and we're actually going to use it in an open loop mode, and we're going to take advantage of that infinite gain from input to output. If you notice here, the definition of voltage gain has always been V out over V in, whether it was closed loop or whether it was open loop. And what we're going to do is we're going to define V in here as the difference between the V plus and the V minus voltages. So V in is going to be V plus minus V minus in this open loop op amp circuit. Therefore, the voltage gain is V out divided by V in, and V in substituting is V plus minus V minus. That's going to be greater than 10 to the fifth, and ideally it's greater than infinity. Very, very large open loop gain. So if you take a look at this and solve for V out here, stay with me. V out is approximately equal to the difference in voltage between the plus input and the minus input times infinity, times a really big number. If V plus is greater than V minus in this expression up here, I don't care if it's a picovolt greater, a nanovolt greater, because of the high gain, if V plus is greater than V minus, this quantity becomes positive, some minute positive voltage. And if you take that times infinity, the output's going to slam to the rail, to the positive rail. It's not going to get there. Your specs tell you it's going to get within 1.5 volts of it, so the output will go approximately to VCC minus 1.5 volts with our amplifier. What about if this quantity is negative, even the slightest bit negative? Well, if V plus is less than V minus up here, no matter how minute, if V plus is smaller than V minus, this is going to be a negative quantity. And the output will be some minute negative voltage times infinity. It's going to slam to the negative rail, VEE. V out will be the negative VEE. It won't get there. It'll get within 1.5 volts of it. We're going to use this characteristic of that open loop gain in the next circuit. It's used in what you call set point circuits. How can this open loop configuration be useful? The answer: in voltage comparator circuits using set points. Control engineers use this constantly. Very, very popular. It's something you really should know when you leave this course. Example: design a circuit that will produce a high active alarm signal called alarm if either the pressure is greater than 800 pounds per square inch absolute or the temperature is greater than 95 degrees centigrade. We talked about this a little bit in the digital class. If you looked at the first lecture, and I said that we would use op amps as comparators in the analog course, well, this is where we're going to actually design this circuit. But before we design the circuit, we're going to go out, we're going to buy two transducers. We're going to buy a pressure to voltage transducer, and we're going to buy a temperature to voltage transducer. And we went ahead and we already talked about these devices. They're nonlinear devices. They have a little bit of S shape to them if you take a look on both of these. But up here you have pressure. We're going to say we went out and purchased it, and let's use it in a linear form. It goes from 0 to 1,000 pounds per square inch, and it's 0 to 10 volts. Where 0 volts is 0 pounds per square inch and 10 volts is 1,000 pounds per square inch absolute. The temperature to voltage transducer is similar. We're going to assume linearity. When it puts out 0 volts, you're at 0 degrees C, and when it puts out 10 volts, you're at 100 degrees C. Now what we want to do is we want to design a circuit that will produce a high active alarm signal if pressure is greater than 800 pounds per square inch or temperature is greater than 95 degrees C. So if you look at the next page, this is the design. Used a lot in control applications. Here we have a pressure signal that's proportional to voltage. We'll call it VP. And where's it coming from? It's coming from this transducer out in the field somewhere. Here we have a temperature transducer that's given us a voltage that's proportional. The temperature is proportional to the voltage, and it's coming from this transducer that we just talked about. What we want to do is we're going to run it into a comparator circuit. Now I want to set VCC up as plus 6 volts, and I'm going to set VEE up as ground. And you can buy op amps that'll do this. Notice that when you get within 1.5 volts of that rail, you're at 4.5 volts out here. But since we purchased these devices to get to the rail, you could bias this at 6 volts or bias this at 5 volts. And it'll work in a digital application. So basically, this is going to be a digital signal out here because of this high gain. If this value here is greater than this value, it'll go to a 1 logic level, plus 6 volts. If this value here is greater than this value, for reasons we discussed in the previous page, it slams to the negative rail, in this case 0 volts. There's your digital signal, high active. When this signal goes high to a 5 volts, the pressure is greater than 800. Well, how do we get that to happen over here? Well, we use a voltage divider, or I'm just going to show it as a battery here, that's called V pressure set point. It's a set point pressure that corresponds to 800 pounds per square inch. 8 volts in our linear device here, 8 volts is going to be our pickoff point to give us 800 pounds per square inch. So all we have to do is set up a voltage on the minus input at 8 volts. That represents 800 pounds per square inch. That's called set point for pressure. Notice that as long as this voltage here is less than that voltage, and it will be if you're at 100 pounds per square inch, 200 pounds per square inch, 500 pounds per square inch, this will be low for the reasons I discussed on the previous page. This voltage will be less than this voltage. This voltage will be more than this. If this is more, you're amplifying through a gain of infinity, a negative voltage that's going to give you 0 out here. So this is not active and you're not producing an alarm. But as soon as this point becomes greater than 8 volts, 8.0000001 volt, this slams to the positive rail, goes to 6 volts. This goes active, you get a 1 there, you get an alarm signal. You can change this set point to anything you want. We have it set up at 8 volts, which represents 800 pounds per square inch. Temperature works the same way. If you take a look down here, we needed a set point of 95 degrees C. If you look at the previous page, 9.5 volts is going to give us 95 degrees C if we assume linearity in this temperature transducer here. So we just set up a battery, but you do it through a voltage divider and a potentiometer. That's the way they do it. You set up 9.5 volts here as a set point. 9.5 volts represents 95 degrees C. As long as this voltage stays more positive than that voltage, you don't have an alarm situation. This does not go active. It stays low. But as soon as this point, as soon as this temperature threshold gets above 9.5 volts, this positive difference here, because this gets greater than this, it's a positive difference. Look at the previous page. Multiplied to a gain factor of infinity, slams to the positive rail. This goes to 1, and a 1 produces an alarm. That's how you use set point to pick off different constant values of pressure, of temperature, of level, of speed. And it's all based on the open loop configuration of an operational amplifier, which some books refer to as a comparator circuit. No, this is not in your textbook, but I want to cover it in this course because it's very important. So make sure you understand that. You're going to see that again. And then the last thing I want to mention is on pages number 90 and 91 and 92. And the only thing I want to point out there, you're not really responsible for all the detail here, but I'm going to talk about input and output resistance, or impedance. Impedance is just AC resistance. You'll find that out in the next 3 weeks. But input and output resistance or impedance of op amps. So we've talked about them. We talked about ideally looking in, Ri is infinity, and looking in from the outside, R out, or RO, we referred to it, was very, very small. We let it go to 0. You're going to have a lab on this. As a matter of fact, 2 of your labs are going to talk about this. And Rin is not the same thing as Ri. I'm going to show you 2 examples down here, and real quickly I'm going to look at these calculations here. But let's look at R. You know what Ri is. Ri was this input resistance here. This input resistance here. Here. It was infinity. Ri was looking in at this point. So when you talk about Ri, you talk about looking into the operational amplifier from this point. When you talk about Ri, you talk about looking at it from that point, looking in. And Ri is what we said, ideally, let it be infinity. And it worked fine through all the analysis. That's what Ri is. Rin is the input resistance of the circuit, looking from the source, looking here, or looking here. Rin and Ri are not the same thing. But in homework and in lab, you're going to have to be able to see this, and I'll show you the quick way of looking at it. Do you see that what I did up here was I got this source resistor and I brought it out and I put it up here in series. And since Ri is infinity, and the only thing between this point and this point is Rs, Rs is negligible. So do you see when you look at a non-inverting amplifier circuit, look at all your non-inverting amplifier circuits, Rin is approximately equal to Ri, which is approximately equal to infinity ohms. I'll let you use that. I'll let you use that as a quick analysis. It's not exactly right. We're going to look at that in a minute. But for now, do you see that Rin and Ri are equivalent from this point to this point? But look down here in an inverting amplifier circuit. This is virtual ground. Ri is still infinity. But if you're out here and you want to know what the input resistance is to that circuit, with this being virtual ground, you see that Rin down here is approximately equal to R1. That's very important. Up here, Rin is approximately equal to infinity. Down here, Rin is approximately equal to R1, because that's virtual ground. What does that tell us? That tells us this circuit up here, that total current flowing in there is approximately equal to 0 amps. That's a really good thing. The circuit's still going to work with the voltages, but it draws negligible current from the source. Down here, if R1 is low, you can get significant current here, because it's just Vs divided by R to get the total current. You have to be careful with the value of R1. You want to make sure it's high enough not to pull too much current from the source and pull this voltage down. Now you know that Rin is not defined the same way as Ri is. They can be close to one another in this circuit. but they're not the same thing. I want to look at additional operational amplifier analysis real quick. And I want to point out to you that this right here is a non-inverting circuit. And with this non-inverting circuit, if you analyze it by looking at that current I in, you can write an equation for I in here. If you write the equation for I in, I want you to notice this right here is just your feedback term. It's your H. It's what portion of this makes it back to here. Well, we know it's a negative because it's coming back. It's negative. We know it's going to be, I'm sorry, there's a negative in the equation here. I know the proportion of this, it's a non-inverting amplifier, so it's a plus voltage here. The plus voltage here that's being fed back is, using the voltage divider, is R1 over R1 plus RF. That's what portion of this makes it to this point. So I'm letting H be R1 over R1 plus RF. If you go through and analyze this, you can see what Rn is in this circuit here. What is Rn for a non-inverting circuit? Well, I already told you that what you could do for a non-inverting circuit, you can basically say Rn is approximately equal to Ri, because it's a series circuit between that point and that point. But why? Well, if you go through the analysis here, you can see that Rn is simply equal to Vn over In, and I made calculations here to form the ratio. Resistance is voltage over current. Resistance in is Vn over In. And if we form the ratio from our expressions up here, you get, this is the actual value for Rn. Rn is equal to Ri times this quantity, 1 plus H times A sub V closed loop. But notice that Rn, in this case, is really, Rn is really greater than Ri. It's greater than the infinity that we were using all along. However, for this configuration, if H is small, if this value here is relatively small, you can see that Rn is approximately equal to Ri if H is relatively small. Because you're taking a real small number here and brings that gain down. So I'm going to let you say for this configuration, for a non-inverting amplifier configuration, I'm going to let you say Rn is approximately equal to Ri. And there's theory behind it. What about for the non-inverting circuit? I do the same thing here for the non-inverting circuit. And to make the analysis, let's go back here and look at this. For the non-inverting circuits, I'm on page 90. I'm going to skip back to 92, find the input resistance there. I make the calculations for this circuit right here. I do the same thing. And you can see down here that Rn is approximately equal to R1 because that's virtual ground. And there's the proof for it. You're not responsible for this. You probably will be in another course. If they asked you for it, there's the analysis just using Kirchhoff's current law, nodal analysis at this point, forming the ratio we need to form, Vn over In. So for this circuit right here, the inverting amplifier circuit, the input resistance is approximately equal to that value of R1, which can get you into current issues. Remember that on some of the homework that I have you do. And then I'm going to go back to page 91. And at 91, I talk about R out. R out is not the same thing as RO. Okay, RO, let's see if I can't stick this in here. We had this little, on both of these circuits here, I'll just show you down here, we had this voltage controlled voltage source, and we had an RO right there. RO is this guy right here. And we said it was very small. But R out is out here looking in this way. R out is not the same thing as looking at that resistance, because there might be resistances here. R out would be looking from this point. If there's another resistance out here and you're looking at R out R out looks from this point in. RO is just that point right there, similar to what we have on the input. But I want you to see for calculating R out and RO here, that R out is approximately equal to RO divided by 1 plus the open loop gain times H. Now, we're not going to use that expression in this course. But if you needed to find the details of R out, and that's looking out here, that's not looking in here to this circuit. This source out here looking back, or this circuit looking back into the left, looking back into that operational amplifier, would see a resistance that would look like this. And you can see that under the best of situations, unless H is really, really small, this denominator here is going to go to infinity, which leaves R out still extremely small value, which is really a good thing. So all they did in this analysis here is they said, how can we figure out what R out is? Well, they stuck a voltage source out here to feed in current, called it IS. In a paper you can do this. They put an ES out here and they fed, and they analyzed that circuit for IS. And then if you just take ES and divide it by IS, which is what they do down here, form that ratio with these expressions you get up here, you can actually get a final expression for what the output resistance would look like out here. All right, and that concludes the lecture.